now we've come in Chapter 6 to a topic called power. So power is defined as the rate at which work is done. It can also be defined as the rate at which energy is transformed. So whenever we see the rate of something, rate always means per time. So we are talking about, when we talk about power, it's the rate at which work is done. So power is going to equal the work done over the time involved. So that's one formula to talk about this thing called work. To call power. Power is a scalar. If you remember, the numbers we deal with in physics are vectors or scalars. Vectors have a direction, scalars don't. So there's no direction associated with power, how powerful something is. It has a unit of W. So there was a scientist, and he was born in around 1850. His name was James Watt, and he gets the unit for power. So he was the scientist who was trying to calculate how powerful the engine, basically, of his horses were. So he took horses out into a field and he hooked them up to plows, and he knew how much work was physically being done because he knew what the force was moving through the distance across the field. He was trying to figure out how powerful his horses were. So when you take the amount of work being done by the horse and you divide it by time, we get this thing called power, which in scientific units, in the standard international units, we will use it as capital letter W. Most places that I've talked about with the power of an engine, we would use horsepower. So you see many TV commercials talking about the horsepower of a car. There are many different devices you might buy, lawnmowers, anything that's basically going to have an engine that's going to spin. They'll rate them usually in terms of horsepower. So the conversion factor is, in 1 horsepower, there's 746 watts. And we don't really need that overly much unless we want to try to see, does the problem make sense to us? Is the engine, is it reasonable? So, for instance, when I watch a TV commercial about a car, occasionally they will say that the horsepower of this engine is 300 horsepower or 400 horsepower. Well, when I do a physics word problem for my car, I very rarely would get those numbers, because what they're telling me on the TV is the horsepower at the engine at something called the flywheel, which is spinning, and here we want to compare it to the overall car. So for the overall car, we're talking about all the different gears that have to be turning to eventually get that car moving. So the horsepower of the whole car, which is spinning the wheels, is not the exact same thing as the horsepower from the flywheel. Okay. So, but we'll talk about that. Mostly in our class, we're worried about the units of watts. Okay, named after a scientist, and his name was James Watt. Now, if I try to derive for a moment, I could say work done is basically a force going through a distance. So I could say this, that power equals, so let me say, the work done could be considered a force times a distance. And I could divide that by time. Okay. If I just look at this piece, well, what is distance over time called? From Chapter 2, we said a distance over time is called the average speed or the average velocity. So another way I could write power would basically be that idea. So this could be taken out and I can put in V average. Okay. So another way I could write power would be power equals a force times V average. So that's a second way I could talk about it. And the book also explains there's a third way that we could talk about it. And the book says that it is equal to the rate at which energy is transformed. So the third way we could look at it is power is equal to, now when we're talking about energy being transformed, we're basically talking about the change in the energy. So we could say this, delta energy over time. Okay. So those three different formulas can help you find how much power is associated with a certain engine. When we talk about power, most of the time we're talking about an engine. A moment ago I just talked about a horse. Well, the horse could be considered an engine. Our bodies, our human bodies could be considered an engine. We can walk around and we can do work. We can push things, we can lift things, we can pull things. A regular car engine gets fed by gasoline, and we need the system to be tuned up every now and then, whatever. Well, our bodies get fed by food, and food is stored up chemical potential energy. So when we eat food, we are feeding the machine, and then we now can do some work. And just like your car, if you filled up your car with gas and then took it for a drive all day long, you would run out of gas and your car wouldn't go. If we feed our body in the morning and then go out and start doing some work, after a while we get tired, we feel weak, we feel depleted of energy, and we have to eat more food to replenish the engine. So you have to be very careful, because when you're doing these problems, like when they say the force down here, you have to be talking about the force of the engine. It's not the net force. It's not like any type of force you want to call it. This would be the force of the engine. And you have to be careful here, because when we did conservation of energy with non-conservative forces, friction was taking energy out of the system quite a bit. So you see, we want to make sure that we are aware of what's happening. This formula is relatively easy to use. If they say there's no friction, then this one is an easy formula to use. If there is friction, you have to be extremely careful. So I would say, basically, use this formula with no friction. Okay, so we're going to use this formula with no friction, no air resistance, we're not going to be dealing with non-conservative forces. Okay, so let's do a couple of problems with this. The problem behind me is dealing with power, and it's a common type of problem you'll see in the textbooks and in standardized physics testing. And it says that we have a jogger who is running up a long flight of stairs in 4 seconds. It says the vertical height of those stairs is going to be 4.5 meters. It says calculate the jogger's power output. I forgot to write one thing up there. It should say a 60 kilogram jogger runs up a long flight of stairs in 4 seconds, and the vertical height is 4.5 meters. Okay, so there's many different ways this one can be done. But we're going to use one of those formulas that we talked about. So which one should be the work done divided by the time? So what type of work is this person doing when they're running up the stairs? Well, they're running up and they're working against gravity. Gravity has a weight on us that's trying to pull us down. So we would have to apply a force that would be going up, that would be equal and opposite. So you see, the runner, while they're moving up vertically, they have to be pushing themselves up, and they're pushing their weight up. So the force they're pushing up with is equal to their weight, which is basically just m times g. And how far are they moving up vertically? Well, we could say they're moving up vertically. They gave us right here the height is 4.5 meters, so we could call that a height. So the distance they're going to move is equal to h for a height. Sorry. The first way we defined power, we said power equals work over time. Well, work is a force times a distance. So this particular person is pushing themselves up with a force of their weight through the distance of the height. So we could say that this would be mg h over the time. So m times g is their weight, h is the height times the time. But if I look at that formula, what formula deals with mass times gravity times height? Well, this formula right here is the potential energy formula, gravitational. The potential energy gravitational. So one of the things I wrote on the board a few moments ago was there's another way to talk about power. Power is the change in the energy over time. Well, that is the change of the energy. If somebody runs up the stairs, they usually don't talk about the speed at which they're running up the stairs. So they usually talk about their average speed. So if you just imagine yourself at the bottom of the stairs. At the bottom of the stairs, a lot of times, you're not moving. At the top of the stairs, a lot of times, you're not moving. So you start off with no kinetic energy at the bottom of a flight of stairs, and you have no potential energy at the bottom, and then you push yourself up. And you push yourself up, and at the top of those stairs, maybe you stop moving for a moment to catch your breath. So you have no kinetic energy at the top, and you have no kinetic energy at the bottom. So the changing in the kinetic energy would be zero. But you are moving to push yourself up those flight of stairs, so you have gained gravitational potential energy. And the gravitational potential energy is the formula m times g times h. Okay? But m times g is just a force, and h is a distance, so that's actually the same thing. That's where work comes from. So for this particular problem, you could use the formula here, saying power equals the work over the time. You could use this formula here, saying the change of energy over the time. You could also use the third formula that I talked about, because I said power. One of the other ways I said it was I said power equals a force times an average velocity. Okay. So the person who's pushing themselves up those stairs, that's their weight of their body, the force they're pushing up with. And what's their average speed? Well, their average speed, if you know the distance you're moving through divided by the time, well, that's your average speed, the distance over the time. So there's three different ways we could do it, and it'll work out the same for all of them. I'm just going to pick this form right here and do it right in the middle. I'm going to just type or write here, power equals the mass, 60 kilograms, times gravity, 9.8 meters per second squared, times the distance vertically, 4.5 meters, divided by the time of this whole thing, which was 4 seconds. So when I use my calculator, that number comes out to be the power equals 661.5 watts. So that's how powerful this person's engine is in this particular activity. So what they're doing is, when you talk about watts, watts is basically an energy over a time. So we could take out that watt and we could say watts is a derived unit, meaning it's based on a lot of other base units. So 1 watt is equal to 1 joule per second. Okay. So when you say someone has a power of 661.5 watts, you're saying that that body is using up 661.5 joules each second. Okay. When we eat food, we get stored up potential chemical energy, and in our world, in my world anyways, I look at the packages on the food, and it's the labels on the packages, I mean, and it tells me how many calories that I am going to consume by eating this food. In some countries, they don't use the word calories, they use the word joules or kilojoules. So kilojoules is telling us how much stored up energy our body will receive as we're eating that food. Well, this person running up those stairs will basically be using up, will be burning off 661.5 joules per second. Okay, so that's the power of that person. Here is a problem, and it says we have a 1,200 kilogram car, and that car is going to go from 0 meters per second to 25 meters per second in 8 seconds. What is the average power produced by the engine, by the car's engine? So just to give you a little insight, my rule of thumb from Chapter 2 was if you see a speed in meters per second, approximately double it, and it'll give you how fast the car is going in miles per hour. So if I double 25 meters per second, that's giving me 50 miles per hour. So this particular car can go from 0 to 50 miles per hour in 8 seconds. I don't know if you're impressed with this particular type of car, because most people usually say things like, my car can go from 0 to 60 in 3.6 seconds or something like that. I don't think this is the best car. Okay, but I digress. We want to find the power by the engine. So you have 3 choices. You can use any of the formulas we've been talking about, because if they don't mention friction, it's not there. So one of the formulas would be this. Power equals the work done over the time. Okay. Now that's one of the ways. So what do we need for this one? Well, work is a formula that says force times the distance. So we would need to find the force of the engine. Okay. And to find that, we would need to know, well, we know the mass, we need to know the acceleration. Okay. So they gave us a final speed, and they gave us an initial speed, and they gave us a time. So using one of the formulas from the constant acceleration Chapter 2, you can find the acceleration. So once you find the acceleration, you'll need to multiply it by the mass, and you'll get the force of the engine. And remember, I just said work equals a force times a distance, so we'll need a distance. Okay. Well, in Chapter 2, if you knew 3 things, like if you knew the beginning speed and the final speed and the time, you could plug them into a formula from Chapter 2, and you could come up with the distance. So you can find the distance, and if you took the force of the engine times the distance divided by the time they gave us, you'll come up with the power. So that's one way to do it. Another way to do it, we could use the other formula here. We could say power equals the force average times the force of the engine times V average. Okay, so to do this one, we once again are going to need the force of the engine. So just like the same time, we'll need to find force of the engine, which will be mass times acceleration. So once again, if you did it this way, you would have to use the 3 givens, initial velocity, final velocity, and time, and you'd have to find the acceleration. Then V average, well, V average is a formula, so V average is equal to the initial velocity plus the final velocity over 2. So you'd have to do these few calculations. If you do these few calculations, then you could plug it into this, and you would get the power. It would be the exact same as power over there. You could use this formula of it. Power is the change in the energy over the time. So, what type of energy are we thinking about when a car is driving along the road? This, in my mind, is a flat road, because they haven't said anything at all about a hill. They haven't given me any angle. They haven't said it's a hill. So in my mind, it's a flat road we're talking about. So if I have a car driving along a flat road, well, that means that the change in the potential energy would be 0. So there's no change in the potential energy. What's the other type of energy we've been dealing with? Kinetic energy. So the kinetic energy formula would be 1/2 mv squared. So if we're talking about the change in the kinetic energy, well, the final kinetic energy would have a final velocity here, and the initial kinetic energy would have the initial velocity here. And then we do that, and we divide it by time. So of these possibilities, usually one is easier than the others. So since this is a video and you're looking at it on your own time, usually in class what I do is I say to the class, before I write all of these things that they're going to need, I basically list the 3 formulas, and I typically would say to the class, here's our problem, and all of these will work and give us the same answer, but I say usually one of them is much quicker and one of them is much easier to do than the others. And so I just say to the class, think about it for a moment, and then let me know, and we'll just do one of them. as in the room. We're not going to do all three. So I just wait until someone says. If someone says, let's do the first way with the class, I'll show them how to do it the first way. And it's not the easiest at all. In fact, I would think the first way might be the hardest, because I have to use some calculation to find the acceleration. Then I multiply the acceleration times the mass to find the net force on the engine. And then I have to go and I have to calculate the distance that the car has traveled through. I don't think that's the easiest. The easiest way in my mind would be using this, the change in the energy, because the only energy is changing is the kinetic energy. So if I did it that way, and I will, that's the way I'll do it here. And if you would, you probably should try to do this problem with all of the ways and see that you're getting the exact same answer. But at least we'll see how to get it in one of the ways. Okay, so the way I want to do it is power is the change in the energy over time, which would equal 1/2 mv final squared minus 1/2 mv initial squared over the time. The initial speed is 0, so that goes out. And so I'm looking at 1/2. The mass of this car is 1200 kilograms. The speed of this car at the end, the final speed is 25 meters per second. I have to square that. I divide it by the total time involved, 8 seconds. So when I plug in those numbers, it comes out to be 375,000 joules divided by 8 seconds. And that's going to give me something when I plug that in. It gives me 46,875 watts. So that's the power of this car's engine. In my world, I don't really identify with the power of an engine in terms of watts by looking at this number, 46,875. It's almost 47,000. To me, it seems incredibly. It's a huge number, it seems, and I need to be able to try to compare it to something in my world. So earlier in the lecture, I gave you the conversion identity between horsepower and watts. So if I do that, take this out of here for a moment. So right at the top here, I've written convert 46,875 watts into units of horsepower. And that would be a unit that I can identify with. So if I just write what I'm given 46,875 watts. If I then go and try to convert this, the identity I gave you earlier was in 1 horsepower, there is 746 watts. So I take this number, the watts will cancel out with the watts down here. Take that number and divide it by 746, and I come up with this, 62.84. I remember when I did this type of a problem for the first time, and I knew a little bit about engines, and I knew a little bit about lawnmower engines, and the TV commercials I had been seeing said that the power of these engines advertised on TV is always in the 300 and the 400 horsepower range. So I was thinking I've done something wrong, but this is the real answer right here. You may say that a lawnmower's engine is more powerful than that. We are talking about the overall car by itself as being the engine. So the overall car is being pushed. When they test the engine by itself, they just test the little piston coming out of the engine and spinning. So they test it at the edge of the engine, which is called the flywheel. They don't test how the whole car overall is working as a machine. So after the flywheel starts spinning some gears, which spin some more gears, which spin some more things, then there's a lot of efficiency lost along the way. They say a typical car is approximately 12 to 13% efficient. So if they're telling me what the power is at the flywheel, then when it goes through all of those different things of trying to move all those different pieces, and we lose some of the power at each of those connections, because one machine would be turning another machine, then basically they say that we lose, if your car is approximately 12% to 13% efficient, then that means we're losing 88 to 87% of our beginning energy, of our beginning power. That basically means that for every dollar we're putting into our gas tank, we're essentially driving, and only 13 cents of it is helping us drive. The other 88 cents, 87 cents is being lost somewhere to friction where things are rubbing against each other. So this is, in fact, not a bad number for the horsepower for the overall car.